This is our video on the ideal gas law, which, if you've ever taken high school chemistry or a different chemistry class, is probably something that you've seen before. It's a little bit different than our individual gas laws. In our individual gas laws, we have been talking about these types of problems over here. Okay, so we've been talking about when conditions are changing. Those are problems like you have a, P1 and a V1, and you're trying to change the volume and figure out what the new temperature is going to be. So those are called changing conditions problems. And you can use your individual gas laws to figure those out. You can also always use the combined gas law. Those are different than the problems we're going to work on now, which are called ideal gas law problems. And the problems we're going to work on now are problems where the conditions are totally stable. There's not a changing set of conditions, it's just one set of conditions. In these problems, you're going to be given a lot of variables, and you need to calculate the missing one. That'll be a little bit similar to before, but we're just going to use the ideal gas law to do that. Okay, so let's talk about how we got the ideal gas law. What I have over on the side here are the relationships that we talked about in our individual gas law videos. And what this is saying is that volume is inversely proportional to pressure, volume is directly proportional to temperature, and here this is Avogadro's law, volume is directly proportional to moles. Now when you put those relationships together, you get something like this. The volume is directly proportional to moles, directly proportional to temperature, but inversely proportional to pressure here on the bottom. But the problem here is that the units don't work out. So let's look at the normal kind of units we use for each one of these variables. For volume, we usually use something like liters or milliliters. For N, that is always in moles. Temperature, it's always going to be Kelvin. And pressure, we can use things like atmospheres, maybe torr, some millimeters mercury, things like that. Okay, well when you multiply these things together, moles times Kelvin divided by any of these units is never going to equal the units of liters or milliliters. None of the units cancel out there. And that's why we need to add something extra to this. If I look at these units, okay, so I'm just going to pick one of each one of these guys. So it would be liters times moles times Kelvin divided by, and I'm just going to go with atmospheres, but it doesn't really matter here. If I want to get these units to work, I have to add something extra in, and what we're going to do is we're going to add this constant R, which has a value of 0.08206, and its units are really funky. Its units are liters times atmospheres divided by moles divided by K. Right? And the reason why those units are so important that way is because the atmospheres would cancel out, the moles would cancel out, the Kelvin would cancel out, and the only thing that I'm left with on this side is liters, which is exactly what I'm left with on this side. When I rewrite that in equation form, what I'm writing is V times N times T divided by P. So that's kind of how I started, but now I also have this constant R on the top. And usually we see this rearranged this way, PV equals nRT. And that might be the most common gas law that people remember if they've ever studied gas laws before. But when we work with the ideal gas law, we need to make sure that we are careful about all the units because we have this constant R. In our individual gas laws, like the combined gas law and Charles law, Boyle's law, we really only had to be careful about temperature, but here all the units have to be very specific. So I'd like to go over which units will work with each one of these variables. Okay. So just remember, R has the units of liters, atmospheres per mole K, and R is something that you're going to memorize. It's on our common conversions list in your course pack. So you want to remember that. So R has these units. We need to make sure that everything else matches those units. So liters is what our pressure is always going to be in. Okay, so I just want to remind us about what R has units of. It's liters, atmospheres per mole K. And R is something that you're going to want to memorize. It's on our common conversions list, so those are the things that you want to memorize. If R has these units, we need to make sure that our other variables match those units. So let's see, liters is what our volume is going to be in, because that matches there. Our pressure is going to be in atmospheres all the time. This. Our N is always going to be in moles, and that was always true. And our temperature, again, is always going to be in Kelvin. Okay, so just a few quick notes before we get into some calculations. We're always going to convert our temperatures to Kelvin. Because we're working with moles here, and we haven't done a lot of that yet, but because we're working with moles, anytime we're given grams, we are going to convert to moles if necessary. To do that, you would use the molar mass. So you might want to get a periodic table out. We haven't used those in a while. And we are going to make sure that all of our other units have the units of R every time we're using the ideal gas law. So liters, atmospheres, moles, and K. Let's do a practice problem. Again, we're going to read the problem and we're going to make sure that we know what all these numbers mean and what kind of variables we'll be looking for in an equation. So we're going to determine the volume. So we are looking for a volume that a sample of 10 grams of hydrogen gas, okay, 10 grams will allow us to get to moles. And how much will it occupy at this pressure? So that's my pressure. Right now it's in torr. We might have to change that up. And then I also have a temperature here. So let's do a practice problem. Again, I'm going to read the problem and I'm just going to write down what variables I have. Then I'm going to try and find an equation that matches those variables. I need to determine the volume. So I'm looking for a volume that a sample of 10 grams of hydrogen. So I have grams. Usually in these problems, anytime we're given grams, we're going to use those to get to moles. So I'm going to need an equation with moles in it. Hydrogen gas will occupy at, and I have a pressure here, and then at 27 degrees, I have a temperature. Okay, now I need to find an equation that has these variables. I have one volume, one pressure, one temperature. That is the ideal gas law, and I know that's true. I'm not going to use any of my P1V1 problems or anything like that because all of those need at least two of one thing. So 2 volumes, 2 pressures, 2 temperatures, something like that. And I don't have 2 of anything at this point, so I know that it's going to be the ideal gas law. Okay, anytime I use the ideal gas law, we need to make sure that our units are in the units that R are going to be in, are constant here. And so the units of R are liters, atmospheres per mole K. So I need to make sure that my pressure is in atmospheres, the volume that I'm looking for will come out in liters, I need my temperatures in Kelvin, which means in our problem, we need to take this torr pressure and we need to convert that to atmospheres, and we need to take this Celsius temperature and we need to convert that to Kelvin. Just to keep us organized here, I'm just going to make a little list of the things we have and the things we want down the side. So we're trying to find volume. We have 10 grams of hydrogen gas. We're going to use that to find moles. I have 765.0 torr. I'm going to use that to find the pressure in atmospheres. I'm going to do that conversion. And I have 27 degrees C, which I'm going to use to find the temperature in Kelvin. So I'm going to go ahead and do those conversions. Okay, the first one is I have 10 grams of hydrogen. I look at my periodic table, I see that each hydrogen is 1.01, so it's diatomic, so we have 2 of them, so it's going to be 2.02 grams per 1 mole. When I do that on my calculator, I got 4.950 moles. Okay, the next one to do is pressure, 765 torr, and there are 760 torr for 1 atmosphere. That conversion and the pressure conversions are on your common conversions list, so again, you're going to want to know those kind of off the top of your head. All right, when I did this on my calculator, I got 1.006 atmospheres. And I should probably be keeping track of sig figs as I go along here. This had 4 sig figs. This is a definition, so it has an infinite number of sig figs. So I'm going to mark that to 4 sig figs. For my mole calculation, this had 3 sig figs. This has 3, so I'm going to mark it to 3. Okay, the next conversion is going from 27 degrees Celsius to Kelvin. To do that, I'm going to add 273.15, and I get 300.15 Kelvin. Okay, for sig figs, this is to the ones place. This is to 2 places past the decimal. This is only going to be to the ones place. All right, so I'm going to write down those numbers over here. I need a little bit more space to write. The pressure was 1.06 atmospheres and 300.15. Okay. All right, so now I can give myself a little bit of space here. Okay, so I'm going to go back to my equation. PV equals nRT. I'm looking for volume, so I'm going to try and get volume all by itself on one side. That means dividing by P on each side. I get volume is nRT divided by P. So those canceled out on that side. Okay, now it's all about just putting the numbers in. For my moles, I got 4.95 moles. For R, it's 0.08206 liters atmospheres per mole K. And then my temperature was 300.15 K. Pressure on the bottom was 1.006 atmospheres. And when I put that into my calculator, I got 121.19. The units are atmospheres cancel out, moles cancels out, K cancels out, so it's liters. So the units of liters. Now let's talk real quick about sig figs. This had 3, this has 1, 2, 3, 4, this has 4. This had 3 sig figs, and this had 4. So it looks like I have 3 sig figs, which would be right there. And so this would be 121 liters. Okay, let's try another problem. We're going to use the same method here. First, we're going to read the problem and figure out what kind of variables we have. We have 1 mole, and it doesn't say what type of gas, but it doesn't really matter as long as we have the moles. It's not like we need to do a molar mass or anything like that. So we have 1 mole, we have a pressure, and we have a temperature. So we have moles, we have a pressure, and we have a temperature. The problem says we are looking for volume. Okay. So again, I don't have any changing conditions. I just have one of each one of my variables, so I know that I'm going to use the ideal gas law. And I'm looking for volume again, so I'm going to divide both sides by P, and I get volume equals nRT over P. What's nice about this problem is that almost everything is already in the right units. I have moles in the units of moles. R, which is a constant, I know what those units are. My temperature is already in Kelvin here, but my pressure needs to be in atmospheres. I have it in millimeters of mercury. I need to convert that to atmospheres. So before I can put that in, I need to do that conversion. But you probably can do this one in your head. If you can't, I'm converting millimeters of mercury to atmospheres, and there are 760 in 1 atmosphere. So that's a 1-to-1 ratio. That works out, and I get 1 atmosphere. The reason why I've written it to 5 sig figs there is because this had 5 sig figs. Okay, now I'm going to put those into my equation. I'm calculating V, and I have my moles. I have R, 206 liters, atmospheres, mole, K. And I have my temperature at 273.15 K. Now I'm dividing by my pressure. It was 1 atmosphere. Okay, so again, for units, moles and moles cancel out. Atmospheres and atmospheres cancel out. Kelvin and Kelvin cancels out. I'm just going to get volume. And when I calculated this, I got 22.414 for sig figs. This had 3, this had 4, this had 5, this had 5. So I'm going to round this to 3 sig figs, 22.4 liters. Now, if you watched the other videos, you would know this number came up before, 22.4 liters. That's actually a really important number in chemistry because it's the amount that 1 mole of gas will take up at STP. So at standard temperature and pressure, 1 mole of gas will always be 22.4 liters. Okay, so on the slide we have some bottles of gas. Okay, they are all at STP. And remember, standard temperature and pressure is 273.15 Kelvin, and 1 atmosphere, that's the same thing as 700 millimeters of mercury. Now, at STP, if you have 1 mole of any gas, so all of these are 1 mole, it will take up 22.4 liters. That's the calculation that we just did. What's interesting about this is that even though each one takes up 22.4 liters, each one has a different mass. Look at the masses here. Okay. So the oxygen weighs 32, the helium is much lighter at 4. So they have the same volumes but different masses. That means that the densities of gases are going to be different. The volumes are the same, the masses are different, so the densities are going to be different. And density is going to be something that we talk about in another video, in our stoichiometry video, but we're definitely going to kind of reflect back on this concept of at STP, if you have a mole, you would know that it's 22.4 liters. And why we kind of talk about this number a lot is that if you're at STP, if the problem you're doing says that you're at STP, 273.15 Kelvin and 1 atmosphere, you can just use a simple conversion of, if you're given a certain amount of moles, you can say that 1 mole is 22.4 liters, and then you would be able to calculate the volume there. So you don't have to go through like a full-blown ideal gas law problem if you are given moles and you need to get to volume and you're at STP. You could also go the opposite way. So it's kind of a fast conversion factor, but it only works if you're at STP. If you're at any other set of conditions, to get between moles and volume, you would need to use the ideal gas law. Okay, so we talked about the ideal gas law. We talked about the units. We talked about the R constant. We did some practice, and we've also talked about how the STP volume of gases is 22.4 liters per mole. If you're looking for some practice problems, you could use your course pack, page 45, which is Gas Law Practice 1, and you would do number 3. And then you could also use page 47, which is Gas Law Practice 2, and you could do number 2 on that page.